So I really want to stress, when we're talking about exponential growth or decay, two things are going on. First thing is, one, there's going to be a model, and the model is always going to be this y equal to c e to the kt. You might use different letters. People sometimes use an a here, or right, we also have a equals pe to the rt, right? This is the exponential growth for the continuously compounded interest, but it is also an example of exponential growth. Let me make one thing smaller here so they can, committing my usual sin of accidentally covering up the chat. Not that anyone's writing anything, but I mean, people did write some things, but don't want to miss things people are writing by having it covered up accidentally. So this is the model, and almost always, whenever we're trying to answer a question about exponential growth, or decay, our job is to find, or I should say, is to first find C and K, and then answer whatever the question is. That's the deal. And let me take a look here. Come on, mouse, get over here. Sure. Yeah. I'm gonna, so we'll do these problems. So last time we did the first one about the bacteria growing exponentially, and and we answered the question about how many bacteria in 5 hours, and then how long population. I want to do another one just because I think it's good to practice. So let's do another one before we do the radioactive waste one. So let's say we have in the beginning, or at first, there are, let's make up a number, let's say 75 bacteria, or bacterial cells, whatever you want to say. And then we know that, let's say 3 hours later, there are, let's make the numbers not too terrible. Let's say there's 100 bacterial cells. How long? We'll ask two questions. How many cells? Well, let's say 7 hours after the beginning. And we also want to ask how long until there are 150 cells. Yeah, that seems reasonable. Okay, so before we can answer either of these questions, we have to find the model. Meaning, not that we don't know the model, we know the model is y equals c e to the kt. When I say we have to find the model, I really mean we have to find the constants c and k so that we actually know the model. And I typically like to make this little table where we know some things. We know some values of time and of amounts. Remember, t is the time that's passed, y is the amount of stuff we have. In this case, it's the amount of bacterial cells we have. So we know that in the beginning, which is time equals 0, there are 75 bacterial cells. We know that 3 hours later, so when time equals 3, there are going to be 100 bacterial cells. That's enough information, as long as you essentially have 2 different data points, that's enough information to figure out what C and K are. We could do the work to find C, and we won't usually, but I will right now. So you could also just say, we know that C is 75. If you know how much stuff you have at time 0, that is your C value. But you could also plug in and say, okay, I'm going to plug in 0 for T and 75 for Y. So 75 for Y equals C times E to the K times 0. E to the 0th power is 1, and C times 1 is still C. So we get 75 is equal to C. Then we throw that into the equation, to the model, I should say. So we're updating our model. The model now is y equals 75 e to the kt. And now we're going to use the other data point when time is 3 hours and the amount of stuff is 100 cells to figure out what k is. So I'm going to plug in 100 for y and 3 for t. So 100 equals 75 times e to the k times 3. And then we're going to solve for k. So I'm going to divide both sides by 75, and now I'm running out of room. So let's go to the other side. So I'm going to take it to the other side. So I've got 100, sorry, not 100. No, yeah, 100, right? 100 equals 75 e to the k times 3. 100 equals 75 e to the k times 3. If we're trying to solve for something that's in the exponent, we're going to end up using a logarithm usually. But before we can do that, we have to get rid of this coefficient. So we're going to divide both sides by 75. So we're going to have 100 divided by 75 equal to e to the 3 times k, or k times 3. Either way you want to say it. I usually write k 3 times k then. You don't have to, but we often like to reduce this fraction. You can either write it as a decimal if it's nice, it's not nice in this case really, or you can reduce the fraction. This reduces to 4/3, right? I can divide the top and bottom by 25. 100 divided by 25 is 4. 75 divided by 25 is 3. That's just going to be a little easier to work with. And then we're going to take the natural log of both sides. So if you have e to the something equals a number, take the natural log of both sides. And this is the part that everyone has to get real comfortable with. When you take the natural log of e to some stuff, you just get the stuff. So the natural log of e to the 3k is just 3k. So the natural log of 4/3 is equal to 3k. And then divide both sides by 3 or multiply by 1/3. It might look nicer to multiply by 1/3. We can say that 1/3 times the natural log of 4/3 is equal to k. This is just a number. It's a positive number because we have exponential growth, but it's just a number. We're going to leave it like this, though. We're not going to get a decimal approximation for it. You could, but I would prefer that you do not. So we're going to now write our model. Our model, which was y equal to c e to the kt, is now going to be y equal to c, which is 100. E to the writing k is always kind of gross. It's e to the 1/3 natural log of 4/3 times t. So there's our model. Y equals c times e to the k times t. Great. Now that we have found the c and the k values, we can answer the questions. The first question was, how many bacteria will there be after 7 hours? So we're asking what y is equal to when t is 7. Right, so if they're giving you a time, we're going to plug that in for time, and then we're going to solve for y. This is usually the easier variety of question. Right, when they tell you how much time has elapsed, and we ask you how much stuff there is. So to solve for this, we're going to get y equal to 100 e to the 1/3 natural log of 4/3 times 7. And without a calculator, there's not much more we can do. We can just leave it like that. We can get a calculator. So this is where you should use the calculator. So I'm going to calculate this. I'm going to do the exponent part first. So I'm going to do the natural log of 4/3. And then I'm going to multiply it by 7. And then I'm going to divide it by 3. I'm getting approximately 0.67. And then I'm going to do e to that power. So e to the approximately 0.67 is giving me almost 2. It's giving me 1.95. So this is going to be y equal to 100 times, sorry, it should be approximately 100 times 1.9566. Sure. Which, just move the decimal over twice, that's going to be 195.66. Which you might be asked to round to some whatever. If you say round to the nearest tenth, it'd be 195.7. If you said round to the nearest whole bacteria, it'd be 196. Okay, so after 7 hours, there's almost 200 bacteria. Second question, and the second question I want to address because I know I've seen people make this kind of mistake before. So the second question, in fact, let's go back to the other side for a second. So the second question asks, how long until there's 150 cells? I've definitely seen people do the following wrong thing. They said, okay, it takes 3 hours to go from 75 to 100. Then it takes another 3 to go from 100 to 125, and then another 3 to go from 125 to 150. So the wrong answer would be 9 hours. We know it doesn't take 9 hours because in 7 hours, we get almost 195, 196. So it should definitely be less than 7 hours. What I'm trying to point out is it's not a linear relationship, right? You can't say every 3 hours it's going up by 25. It's not. Hopefully you guys remember yesterday when I showed you that first example, and we're like, oh yeah, every time you increase the amount of time by the same amount, you increase the amount of stuff by an increasing amount. That's the hallmark of exponential growth. The time intervals can be the same, and the amount of stuff you have over here is going to be wildly different. Yeah. So to figure this out, we're going to say, well, I want to know how much time it takes to get to 150 bacteria. So I'm going to set y equal to 150. And it's going to be 150 equal to, sorry. Did I make a mistake somewhere? I think I might have made a mistake somewhere. It's okay. Let's double check. Is it y equals 100? Sorry, I feel like I might have done something dumb. I did. It's okay. It's okay. But I think, no, I guess, yeah, I did. It definitely did. For my model, I put 100 here. Pain. Right, but for we actually had that C was equal to 75. I'm not sure what pain means, Alessandra, but I feel pain. Yes, I made a mistake. I'm sorry. So the mistake I made was that I accidentally used 100 here instead of 75, which is actually not terrible as far as mistakes go. We can fix it really easy. F in the chat. I really have no idea what you guys are saying in the chat. That's okay. I don't have to know everything that's going on, but what we should actually have had here is 75. So these numbers should have been 75. Sorry about that. Well, you're doing a very good job. It's okay. I don't need to know all the lingo. So what the answer should have actually been was about 75 times that, which is going to be, let's see, approximately 146. So yeah, it's 146.7. Which actually is kind of interesting because it's almost the answer we're going to get. So doing this next part, we should be like, well, it should be close to 7 hours, right? Because in 7 hours, we get to 146. So our answer here for how much time it takes to get to 150 should almost be exactly that. It should be a little bit more than 7 hours. We should still do the work, but we already have an idea what the answer is going to be. So let's put 150 equal to 75. That's what happens when you flip boards, you're not paying attention, you get things mixed up. 75 e to the 1/3 natural log of 4/3 t. And definitely, so solving for t is going to be more work, right? Finding y, if they tell you the time, you just plug it in, you get a number out, assuming you don't make a dumb mistake, like using 100 instead of 75. But when you're solving for the time, when they say you've got 150 cells, how much time does it take to get there? That's when it's going to take a bit more effort. So the process is always the same, though. In fact, the process is almost essentially the same as what you did when you solved for k. We're going to divide both sides by the coefficient, then we're going to take the natural log of both sides, then we're going to isolate the variable. So I'm going to divide both sides by 75. 150 divided by 75 is 2. So I'm going to get 2 equal to e to the 1/3 natural log of 4/3 times t. And then we're going to take the natural log of both sides. And I guess I'll write it up here because I'm out of room. So if I take the natural log of both sides, I get the natural log of 2 on the left, and I get the natural log of e to the 1/3 natural log of 4/3 t. Now, I don't think you need to write all this, because eventually you're going to do it enough times and you'll be like, oh, the natural log of e to the power is just the power. So you can kind of skip this step if you want to say, oh, the right-hand side is just going to be the 1/3 natural log of 4/3 times t. And then solving for t is really straightforward. You could say you're going to divide by all this, but I would rather, instead of dividing by 1/3, I'd rather just multiply by 3. So I'm going to multiply both sides by 3 and get 3 natural log of 2 equal to the natural log of 4/3 times t. And then divide both sides by 4, natural log of 4/3. So the 3 natural log of 2 divided by the natural log of 4/3 is equal to t. So that would be our precise exact answer. And this doesn't simplify. I mean, I guess if you really, really wanted to, you could break apart the bottom as the natural log of 4 minus the natural log of 3. There's no good reason to do that, though. That's the only simplification you could do. Other than that, this does not simplify. And again, I wouldn't do that. I don't think it's really simplified. So if we plug this into a calculator, 3 times the natural log of 2 is about 2.07, and then divided by the natural log of 4/3, we expect to get something just a little bit more than 7 hours. I got 7.22 hours. So good, that seems reasonable. Okay, so that's what this is kind of going to always be the process. You're going to find the model by finding your C value and finding your K value, and then you're going to answer whatever questions by plugging in either the time value they've given you or the amount value they've given you and solving for the other thing. So let's look at more examples. Where'd you go? I'm sorry, I'm getting lost in my notes here. There we go. So most examples we look at are examples of growth, right? Populations, money, bacterial cells. But radioactive waste is an example of exponential decay. And let me write down the problem. So radioactive waste is often dumped in the middle of the desert and left to decay. I guess that's probably possibly true. But radioactive decay as time goes on, we're going to have less and less radioactive material, where it's going to dissipate. And there's this idea of there's this thing about a radioactive substance called its half-life. And the half-life of a radioactive substance is how long it takes for only half of it to remain, or for half of it to decay. Right? You can't use either word there, because if there's half gone, there's half left. So let's look at this example. Let's say we have a 12-gram sample of radioactive material. And we don't know its half-life, but we do know that it decays down to only 10 grams in a period of 25 days. So we start off with 12 grams, 25 days later, we have 10 grams. And the question we want to ask is actually, what is the half-life? So how long would it take to get to 6 grams, right? Because that's half of what you're starting with. So let's make a table. I always think it's worthwhile to make this table because it tells me what to plug in where. I suppose I should say, let's write down the model. The model is still the same. Y equals C e to the KT. And then we're going to make our little table here. We have time and amount of stuff. Oh, by the way, some books like to use a little m. So some books, instead of writing y equal to c to the kt, specifically like calculus books for radioactive decay, they like to write it as m of t equals m naught times e to the kt. The m being for the mass of the stuff you have. It's the same formula, whether you're writing m of t equals m naught e to the kt or y of t equals c e to the kt. It's the same thing. It's just using different letters to represent things. So at time 0, right in the beginning, there were 12 grams. And then 25 days later, there were 10 grams. Here's what I want to say. If you went 25 days later, you would not have 8 grams. I want to make that really, really explicitly clear. Actually, I could tell you how much we have though. So the thing is, if the amount of times are the same, it's the proportion that you're going to have, or the multiplication factor. So from here to here, 25 days later, I have 10/12 of what I had before, or 5/6 if you want to reduce that fraction, right? To get from here to here, you times by 10/12. 12 times 10/12 is 10. So if the same amount of time passes, the same amount of multiplication factor happens. So we'll check this later just because I think it's worth checking. But if 50 days pass, we should have 10 times 10/12, which is 100/12 grams, which is about, I think, 8.333. All right, yeah. I think. Now I need to check. 100 divided by 12. Yeah, 8.333. So, right, more than 8 grams. So you're not changing by the same amount each time, you're changing by the same multiple each time, which is interesting. But again, not something you need to super worry about. So let's find the model, meaning let's, oh, I know, yeah, okay, that's fine. Let's plug in the things. So I think I'm going to skip step of solving for C and just say, we know that since time equals 0, we have 12 grams, C is equal to 12. So we've got Y equal to 12 e to the KT. And then we're going to plug in the other data point where the time is 25 days and the amount is 10 grams to solve for K. So we're going to set 10 grams equal to 12 grams times e to the K times 25 days. And then we're going to solve for K. So let's divide both sides by 12. So 10 divided by 12 equals e to the, I'm going to write this as 25 times K. That's pretty standard. And then we're going to take the natural log of both sides. I'm going to do actually 2 things. I'm going to reduce 10/12 to 5/6. I'm going to take the natural log. So the natural log of 5/6 equals the natural log of e to the 25K. And everybody at this point should be able to tell me, you can even type it in the chat. I would like you to type it in the chat. What is the natural log of e to the 25K? Right, you guys knew the question before I even asked it. Exactly. So that's exactly what we've got. The natural log of 5/6 is equal to 25K, and then divide both sides by 25 or multiply by 1/25. I think it's kind of, so you could write it as the natural log of 5/6 over 25. I feel like that gets a little messy. I think it might be nicer, although really either way is fine, to write it as 1/25 times the natural log of 5/6. Whatever your preference is, I don't care, as long as it's right. So let's not make the mistake that I made last time of flipping the board over and then making an error. I'm going to erase some of this question. So the only thing left now is to answer the question, what is the half-life? So to answer that question, we have to know what a half-life means. So the half-life is the amount of time it takes until there's half left. So we're really wondering is, what time when half the substance remains? Okay, well, that's easy enough to put in our table here. I'm trying to get down to, well, if I want half to remain, I'm trying to get down to how many grams? Well, I started with 12. Half of 12 is 6. So I'm trying to figure out what time is it when there's 6 grams left. So we're going to plug in 6 for Y and solve for T. That's what we're going to do. So let's see, my model. You don't have to write the model, we could. So here's our model where C is 12 and K is 1/25 natural log of 5/6. So our model is Y equal to 12 times e to the 1/25 natural log of 5/6 times T. Hopefully you guys can see this okay. 1/25 natural log of 5/6 times T. Sometimes if it looks kind of gross, I put it in brackets so that we don't get too terrible. And then we're going to plug in, right? We're going to plug in 6 for Y and we're going to solve for T. So let's just go ahead and replace Y with 6. So I'm not going to write it again. First thing we're always going to do is divide by that coefficient there. 6 divided by 12 equals e to the 1/25th natural log of 5/6 t. Notice, this is always true. When you're finding the half-life, once you divide by this here, you should always get 1/2 on this side. That will always happen if you're looking for the half-life. So then the left side is 1/2, and we're going to get the natural log of 1/2 equal to the natural log of e to the 1/25th times the natural log of 5/6 t. And I'm really okay with you skipping writing this and just writing that it's equal to 1/25th natural log of 5/6 t. Right? We know the natural log of e to a thing is just the thing. So I've got that the natural log of 1/2 is equal to 1/25th times the natural log of 5/6 times t. And then I'm going to erase here. We can solve for t by multiplying both sides by 25 and dividing both sides by natural log of 5/6. And that is our answer. That is the half-life. For that to be meaningful, we should probably throw it in the calculator to see what we actually get. In fact, I don't actually have to do that though, because I've already written it down over here. We get that t is about 95.04 days. This is approximately 95.04 days. So in 95 days, we'll have half of what we had. And that's true no matter what we're starting with. So from the beginning, in 95 days, we'll have 6 grams. And then in another 95 days, we would have 3 grams. And then in another 95 days, we would have 1.5 grams, right? When you're talking about a half-life, or comparatively like a doubling time for a different population growth example, the doubling time or the half-life time is always the same, meaning it takes a certain interval of time for a population to double. And then that's always the case if you're talking about exponential growth. Similarly, it takes a certain amount of time for a radioactive substance to decay by half, and that's always the amount. So, right, if I said after 25 days, how long does it take to decay from 10 grams to 5 grams? It would be another 95 days, because 95 days is the half-life. And so then just to come back at this question to kind of see that I was actually not lying to you. How much stuff do we have after 50 days? Well, I said it should be 100 over 12. Let's see if that's actually true. And yeah, this is way too much. So let's actually go over the other side. Just because it's kind of interesting. So my model, y equals 12 e to the 1/25th natural log of 5/6 t. If we want to know how much radioactive material there is after 50 days, we're going to get y equal to 12 e to the 1/25th. I guess I could have just put 50 in there. Natural log of 5/6 times 50. And here's kind of something interesting that happens when you have essentially a multiple of the number of days that you know it takes to do something. 50 times 1/25th is 2. This is 12 times e to the 2 times the natural log of 5/6. Okay, we'll check this out. This is where I'm going to use a rule for logarithms here. I'm going to say that this power of 2 can come up as the power on 5/6, right? Because if you have a constant times a logarithm, that constant can be the power of the stuff inside the logarithm. So this is equal to 12 times e to the natural log of 5/6 squared. All right, so let me ask you guys, what's e to the natural log of some stuff?
James, I have a quick question.
Yeah, go ahead.
Where'd you get the 2 from?
So 50 times 1/25th.
Okay, thank you.
Right. 50 divided by 25 is going to be 2. So when you take e to the natural log of some stuff, you just get the stuff, right? It's actually the same kind of idea as the fact, right? If you had the natural log of e to the 5/6 squared, that would also be 5/6 squared. Same idea. If you do the natural log of e to a thing, you get the thing. If you do e to the natural log of a thing, you get the thing. But look, this is just 12 times 5, 6 times 5, 6, which is literally how I calculated the thing before. This is 12 times 25 over 36, which is just 25 over 3, which is 8.333. So the thing I'm trying to make clear. So again, I wouldn't worry too much about like how I simplify this exactly. Like I'm not usually going to ask you to do this, but it is a true fact. If you know how long it takes for something to multiply by a certain amount, that is always true. Let me give you another quick example of this just because, there's one other thing I wanted to say that's kind of important. Sometimes people get caught up when it's radioactive decay, but there being a negative K. I don't do that. You can if you want to. But the thing I want to say here is that our K value is negative, right? When you're talking about exponential decay, radioactive decay, exponential growth / decay, but specifically decay, this K value here is a negative number because the natural log of 5/6 is definitely negative. In fact, the easy way to see this is to say, oh, well, of course, the natural log of 5/6 is just the natural log of 5 minus the natural log of 6. And that one's bigger than that one, so of course it's negative. But whenever you're doing a decay problem, you will always get a K value that is a negative number. And that's what should happen. But what I'm saying you do not have to do is you don't have to do this thing that some people like to do where they say it's CE to the negative KT. You can if you want, it'll still work out the same, but you do not need to do this for me. You can do it for you, don't do it for me. I would encourage you to not do it this way. I think this is kind of extra confusing personally. I would just do it the way we've been doing it. So let me give another example. This is an example that's also not in the notes, which is fine. Yeah, it's fine. We got lots of time. Actually, the next example, I guess, kind of gets at that. But I kind of want to do it different. Oh, sure, fine. We'll do the next example. So, this one is a little annoying with the time frame. So, example. 2 months ago, we had some mice, 3 mice. Now we have 18 mice. I'm going to change the question actually. Assuming the population grows exponentially, so assuming exponential population growth, how many mice will there be 4 months from now? Okay, so here's what I find mildly annoying about this problem, but it's something that we have to deal with sometimes. The now time isn't the beginning time, which is unfortunate. We can adjust. So here's what we're going to do. We're going to make our little table of time and the amount of mice. And then we're going to say that now is going to be time equal to 2. And 2 months ago is going to be time equal to 0. You usually want your first known instance of something being like, of us having a known time. We usually want that to be your 0 because it just makes everything easiest. And so then if I want to know how many mice there are 4 months from now, I want to know how many mice there are when time is equal to how many months? Well, 2 months, 4 months later, it's going to be time equal to 6. Right, so 4 months from now, if now is time equal to 2, 4 months from now is going to be time equal to 6 months. And then we know some stuff. We know that 2 months ago, the amount of mice was 3. And then now, when time equals 2, the amount of mice is 18. And we want to know how many mice there are 4 months later. And I'm going to kind of show you two ways of doing this. So here's the thing. If we know, or if we're given a problem where in some interval of time, the population multiplies. Let me ask everybody, what did the population multiply by to get from 3 to 18?
6.
Right. So we know that in a 2-month period, the population multiplies by 6. Well, time equals 6 is a couple 2 months. It's a couple 2 month. Oh my God, is a couple 2 month periods later. So I can say that from time equals 0 to time equals 2 to time equals 4 to time equals 6. We know that at time equals 0, the population is 3. And then it's going to multiply by 6 to give us 18. But in this next 2-month period, the same thing happens, right? In a 2-month period, the population multiplies by 6. So 18 times 6 is going to give us, let's see, 108. And then in the next 2-month period, the population is going to multiply by 6 again. And 6 times 108 is 448. So if you happen to see, this doesn't happen frequently, but if it does happen where the amount of time later from your now time is exactly an integer multiple of the interval you were originally faced with, you can use this rule, this fact that, oh, well, the population is just multiplying by 6 every 2 months. So from here to here multiplies by 6, from here to here multiplies by 6, and from here to there multiplies by 6. That is something that can be exploited. I'm still going to show you how to do this one the long way, because this isn't something we always easily remember, but it is something that is true. So let's do it the long way. So here's my setup. Y equals 3e to the kt. Right? I know my c value is 3 because when time equals 0, y is 3. And then we're going to solve for k by plugging in the later known value. So I'm going to write this as 18 equal to 3e to the k times 2. Divide both sides by 3 so that we get 6 equals e to the k times 2, or 2 times k. Take the natural log of both sides. Okay, I'm going to not write the natural log of the right side. I'm going to write the natural log of 6 equals the natural log of e to the 2k is just 2k. And then finally divide both sides by 2. So that k is equal to the natural log of 6 divided by 2. All right, and now we want to answer the question, how many mice are there 4 months from now when t equals 6? Again, setting up your frame of reference at the time is important so that we get things right. So we plug in 6, so write the model. So the model is y equals c, which is 3, e to the k, which is natural log of 6 over 2, t. Can't simplify that really. I mean, just is natural log of 6 over 2. And then we're going to plug in time equals 6. So we're going to get y equal to 3 e to the natural log of 6 over 2 times 6. You could either plug this into a calculator, but in this case, we can actually simplify this, right? 6 divided by 2. And so this is where we have to make the observation that, oh yeah, this 6 is a integer multiple of 2, which is the initial interval of time. So we're actually getting this is 3 e to the 6 divided by 2 is 3. So we've got 3 times natural log of 6. Well, this is going to be, and again, I'm going to do that kind of trick where we write 3 times natural log of 6 as natural log of 6 to the 3rd. This 3 comes up as the power. But then e to the natural log of 6 cubed is just 6 cubed. So this is equal to 3 times 6 cubed. Or if you prefer, 3 times 6 times 6 times 6, which is going to be exactly, I feel like I might have made a small mistake here. That feels right. 216. I should check my math here just to be sure. It's not like I didn't make a conceptual error. I just feel like I made an arithmetic error here. Oh, I made a mistake here. You guys let me get away with it. If you see mistakes, call me out. 108 times 6 isn't 448, it's 648. Sorry. And this 3 times 6 cubed is 648. So for one like this, if you recognize that the amount of time intervals is some multiple of the original time interval from the initial time you're given to the later time you're given, you can just say, oh, we're going to multiply by the same amount each of those time intervals until we get to the value we want, which is kind of cool. Yeah. It also works for exponential decay. I'll just give you a real quick example of that before we do this last question here. So let's say that the half-life of a 30-gram radioactive substance is 11 days. How much will we have? Sure. 44 days after the beginning, after initially observing it. Well, again, you could do the whole thing, which we're not going to do this time, where you find C, you find K, and all that jazz. But in this case, you can say, oh, well, look, I know that at the beginning, I have 30 grams. And then 11 days later, well, since the half-life is 11 days, I'm going to have 15 grams. And then 11 days later, I'm going to have half of that, which is 7.5 grams. Or if you prefer the fraction, 15 over 2. And then 11 days later, I'm going to have half of that, which is either 3.75 grams or 15 fourths. And then finally, another 11 days later, I'm going to have half of that, which is 15 eighths, whereas the decimal is 1.8625, I think. 3.6. Yeah, that seems right. Okay. Yeah, now I'm like, sure, doesn't matter. It's fine if it's not exact. He says as he's still trying to make it exact. Anyway, it's not that important. I can like, it's not that important, but I'm like, but secretly it's super important. Anyway. Sorry, I know it's dumb, but I have to have it right. No, it's 1.875. I knew I was doing something dumb. Yeah, thank you. Calculators are good tools. We should use them. No need to make silly errors. So, but the point is, right, we didn't have to actually do the whole finding the C and the K and all that jazz because the amount of time we're asked about happened to be exactly a multiple of how long a half-life was. So we just say, oh, it's 4 half-lives, so we're going to decrease by half 4 times and get that amount there. Okay. Yeah. So one more, just because I think there's a problem like this in the homework, and I wanted to make sure to do an example like it. So the last one is, I've written this not very well. I feel like there's more to this problem than I've written in these notes here. So we have a population growing exponentially. And in 1 week, the population increases from 20,000 to 30,000 people. The question is, or 20,000, I think this problem is in the guise of infectious disease. So 20,000 people infected with the disease to 30,000 people infected with the disease. I'm sure this wasn't the example I came up at the beginning of this year. probably was. People infected. So the question we want to ask is, what is the percent increase? Oh, I know why I'm asking this question. Of the number of people. So the percent increase, well, literally there's 50% more people infected, right? So we do 30,000 divided by 20,000. That's going to give you 1.5 or 150%. So the percent increase is a 50% increase. But what I want to point out here is that just because you, so if I said, write the model using this, the model is not going to be y equal to 20,000 e to the 1.5 t. Your percent increase is not the same as your rate of growth because your percent increase is slightly different. It's similar, they're not like far from each other, but to find k, we can't just assume it's this 1.5 value. What we have to do instead is use the data. So we know that at the beginning of the week, time equals 0, the amount of people is 20,000. And depending on how we want to measure time, we can say 1 week later for measuring time in weeks, or you could say 7 days later for measuring time in days. We have that the population is 30,000. So we can say, all right, we know that our C value is 20,000. And then we know that when the Y value is 30,000, it's equal to e to the k times 1. Well, that's going to be easy to find k, right? We're just going to divide both sides by 20,000. So you're going to get 30,000 divided by 20,000, which we know is 1.5. So we're going to get 1.5 equal to e to the k. And if we take the natural log of both sides, the natural log of 1.5 is equal to k. So here we're actually getting that k is the natural log of 1.5, which is about 0.405. So 50% increase, but the rate of growth is more like 0.40 or 40%. So that's kind of what's happening with this difference here. Now, so I really want to make it clear that if someone tells you how much the percent increases, we can't just use that for the k value. We have to do this kind of thing where we say, okay, we're going to use this data. We know that in the first week, the increase is 50%. But the thing is, in the next week, the increase is not going to be 50%. It's going to be something else. So, or actually, the increase is going to be 50%, but that doesn't mean that k should be 1.5 or 0.5 or anything like that. It has to be the natural log of 1.5. So that the equation actually works out right. That's what I'm actually trying to say. So here our model would be y equal to 20,000 e to the k, which is natural log of 1.5 times t. And this equation would show a population increasing by 50% every week. Yeah.
I have a question.
Go ahead, yeah.
How did we get from 150% to 50?
To 15?
So it says when we did 30k divided by 20k, we got 1.5 or 150%. But then you wrote that it's a 50% increase.
Right, because if you multiply by 150%, you increase the population by 50%. Right? If we go from 20,000 to 30,000 people, 50% of 20,000 is 10,000. So we've increased by 10,000. It's really more of a language difference than a mathematical difference.